In measure theoretic probability or measure theory, we have seen many theorems, or those are sometimes they are known, famous. They are they are well known by the name lemma. A few such lemmas are there, and two very important lemmas are Fatou's lemma and Borel-Cantelli lemma. So we have seen the application of Fatou's lemma while proving a few theorems. But those are again very standard theorems, and we have proved Borel-Cantelli lemma. Probably we have seen one or two results in this sequel using Borel-Cantelli lemma. But today we are going to discuss few problems that can be solved, that we are going to solve, and which will demonstrate how one can use Fatou's lemma, how one can use Borel-Cantelli lemma depending on the situations. But above all, we should not forget the old and standard inequality, another inequality which is called triangle inequality. So, as triangle inequality one can use anywhere you want, and that will actually in Fatou's lemma we have seen that there is one kind of inequality, and in triangle inequality also there is an inequality. So, is it possible to consider these two together in the sense that suppose on a quantity we apply triangle inequality and then we apply Fatou's lemma, or the other way around. So our discussion will be in that direction to apply or application of Fatou's lemma, Borel-Cantelli lemma, etc. To a few specific problems. So we will discuss 3-4 problems today. The first one will be on product space, and the rest of the problems mainly deal with Fatou's lemma, or under what conditions, or there are some situations I am going to describe when we can apply Fatou's lemma and can get the results very easily. And there will be another problem where we have to apply Borel-Cantelli lemma. So the first problem is that let us first consider a product measure space. And as we know that any measure space has 3 quantities. One is say big omega, another is a sigma field generated by that big omega and measure defined on omega and the sigma field. So product measure is coming from 2 different measure space when combined together in a certain way. So in this case we assume that the main set, or the big set so to say, is R cross R. There is a real line cross real line, and then sigma field generated by script B over R cross script B over R. There is a Borel sets over R, and consider the cross of 2 such things and generate the sigma field. And there are 2 measures, mu L cross mu L, we get the one measure or the product measure. So in a word we have R cross R comma sigma script B over R cross script B over R and mu L cross mu L. So let us consider a set D which consists of paired observations xy, paired values, such that xy belongs to R cross R, such that x equals to y. All we have to show that D belongs to sigma field generated by B over R cross B R and mu L cross mu L of D. That is, if we take this product measure on D, it will be 0. That's all we want to prove. Proof is not really very difficult. Only thing we need to know the few properties of this product measure space, and we have to apply them. The first one, let us consider the lambda as mu L cross mu L. That's the product measure. Now consider 2 things. One is D naught. D naught is xy, the set xy, such that xy belongs to 0 1 cross 0 1. We take all the intervals as closed intervals. 0 1 closed cross 0 1 closed interval, such that x equals to y, and a sequence of sets, that means for every n belongs to the set of natural numbers, and a sequence of sets for every n belongs to z, such that dn equals to, again xy belongs to n plus 1, again closed, n to n plus 1 cross n to n plus 1, such that x equals to y. So these are the 2 things we have defined. One is a sequence of sets, another is one set. Now we know that Lebesgue measure is translation invariant. We can immediately have lambda of d naught equals to lambda of dn for all n belongs to the set of natural numbers, and capital D equals to union of capital Dn, n belongs to z. Actually z or n are basically same, so sometimes I use z and sometimes I use n. So at least in this problem. So that's how we can get the lambda measure or the product measure over d naught and dn for every n. Now it is enough to show that d naught belongs to sigma field generated by script p over r cross script br, and lambda d naught equals to 0. This is all we have to show. Now d naught is basically the 0-1 interval. So let us do one interesting thing, that is let us divide 0 to n closed interval into 2 to the power n sub intervals. 2 to the power n belongs to set of natural numbers. So we denote these sub intervals as in, 1 equals to 0 to 1 by 2 to the power n closed, in, 2 equals to 1 by 2 to the power n, 2 by 2 to the power n, again the closed interval, and so on, in 2 to the power n equals to 2 to the power n minus 1 by 2 to the power n, 1, that is 2 to the power n by 2 to the power n. So this is the way we define 2 to the power n sub intervals. Now let us denote Sn as union k equals to 1 to 2 to the power n in, k cross in, k. So it is immediately clear that d naught is nothing but a limit of Sn as n goes to infinity. This is easy to check. Again, for each n belongs to the set of natural numbers, and for k equals to 1, 2 up to 2 to the power n, it is clear that in, k belongs to the Borel sigma field generated by R. Again, for each n belongs to the set of natural numbers, and for k equals to 1, 2 up to 2 to the power n, it is clear that in, k belongs to the sigma field, that is Borel sigma field generated by R. Then by definition, so since each k belongs to script b of R, then by definition we can immediately say that in, k cross in, k belongs to sigma field generated by br cross br. And naturally Sn, so what is Sn? Sn is some kind of union, and hence Sn is some kind of union of these intervals, these sets ink cross ink. Since each ink cross ink belongs to sigma field generated by script br cross script br, then Sn must belong to sigma field generated by this thing for every k equals to 1 to 2 to the power n, and n belongs to script n, or n belongs to the set of natural numbers. Therefore, immediately we can say that d naught, which is nothing but the limit of Sn, it will also belong to sigma field generated by b script br cross br. So the first part is complete. Now note that Sn is decreasing in n, and limit Sn equals to as n goes to infinity is d naught, which is nothing but intersection n equals to 1 to infinity Sn, since Sn is decreasing. So we have lambda of Sn is equals to summation k equals to 1 to 2 to the power n, lambda of ink cross ink. Now lambda of ink cross ink is nothing but 1 by 2 to the power n into 1 by 2 to the power n is a product measure, and if you simplify, it becomes 2 to the power n into 1 by 2 to the power 2n, which is equals to 1 by 2 to the power n. Now naturally it follows that lambda d naught is less than equals to lambda Sn, which is equals to 1 by 2 to the power n. We have just proved it. For every n belongs to the set of natural numbers. Now if we let n goes to infinity, because d naught is nothing but the limit, so this automatically implies that lambda of d naught is equals to 0. So that completes the entire proof. So basically it's not very difficult. All we need to see the intervals and basically the sub intervals, and look at what is the measure of on each intervals, and to extend it on the product measures. So that will give us the idea of this proof. Now next problem is very interesting in the sense that let fn and gn be two sequences of real valued functions, and f and g are real valued functions such that fn goes to f pointwise almost everywhere, gn also goes to g pointwise almost everywhere, with mod of fn less than equals to gn almost everywhere, and integral over integration gn d mu goes to integration g d mu. Under these conditions, we have to show that integration fn d mu goes to integration f d mu. Note that this condition is very important. Modulus of fn less than equals to gn. So how to prove this? First note that gn greater than equals to mod of fn, which is equals to mod of fn minus f plus f. We can write this. Then by triangle inequality, we can immediately have mod of fn minus f less than equals to gn plus mod f, which implies gn plus mod f minus mod fn greater than equals to 0. Minus mod fn minus f greater than equals to 0. Now we just apply Fatou's lemma directly. By Fatou's lemma, we can immediately write integration g d mu plus integration mod f d mu. Now integration g d mu is nothing but limit of gn plus mod f minus mod fn minus f of d mu, which is less than equals to limit integration gn plus f minus mod fn minus f d mu. This is the place where we applied Fatou's lemma, and this is equals to limit integration gn d mu plus integration mod f d mu, because there is no n, minus, since limit of minus something, it will be minus of lim sup integration mod fn minus f d mu, which is equals to, again, as gn is integration gn d mu goes to integration g d mu, we have integration g d mu plus integration mod f d mu minus lim sup of integration mod fn minus f d mu, which immediately says that, because this left hand side, the two terms in the left hand side cancels with the two terms in the right hand side, so it immediately says that lim sup of actually the third term should be 0. That means integration mod fn minus f d mu goes to 0. Now again, all you have to show that integration of fn d mu goes to f d mu, so there should be a mod beyond that. That means we start with mod of integration fn minus integration f d mu equals to modulus of integration fn minus f d mu, which is naturally equals to integration mod of fn minus f d mu, and that goes to 0. This is what we just proved it, which means that integration fn d mu goes to f d mu. So the proof is complete. Now in a similar speed, we consider another problem. Let fn be a sequence of non-negative Lebesgue measurable functions on 0 to k. It's an open interval, but for a fixed k is fixed. This is very important. K is fixed and belongs to R plus. That means the positive half of the real line. It's any real number but fixed real number, such that fnx goes to fx for almost all x belongs to 0 to k. 0 to k is an open interval. Now let us consider another function capital Fx, which is equals to 0 to x f d mu and fnx 0 to x fn d mu. Then show that integration 0 to k small f plus capital F d mu less than equals to lim inf n goes to infinity 0 to k small fn plus capital Fn d mu. Again, looking at this thing, because there are two interesting quantities. One is this less than equals to, another is lim inf. So these two quantities trigger the idea of using Fatou's lemma into this problem. So we have the idea that probably we can use Fatou's lemma. I'm not sure whether it is going to be correct or not, but let's see. Let's see what we can get using Fatou's lemma. So capital Fx equals to integration 0 to x f d mu. Now f is, again we can write instead of lim inf fn. So now apply Fatou's lemma, we get less than equals to lim inf of integration 0 to x fn d mu. Now integration 0 to x fn d mu is nothing but capital Fn x. So capital Fx is less than equals to lim inf capital Fn x. This is one result that we got immediately. Again we have to use Fatou's lemma. Let's see. So 0 to k small f plus capital F d mu, which is less than equals to, just now we have seen that integration capital F d mu is less than equals to lim inf fn d mu. So just write down that thing. So there should be an inequality sign, and f is again fn is a sequence which converges to f. So this is equals to integration lim inf fn plus capital Fn, and that is again less than equals to limit, because of Fatou's lemma, limit 0 to k, integration 0 to k, small fn plus capital Fn d mu. So that completes the proof. So it is very elegant to see that how simple lemma like Fatou's lemma, how strong it is, and we can apply this maybe sometimes repeatedly in order to get the result very easily. So the last problem that we are going to discuss today is another very interesting problem based on Lebesgue measure. So let alpha be a real number, and let us define E, another set E, is that x belongs to the closed interval 0 to 1 such that modulus of x minus p by q less than q to the power minus alpha for infinitely many pq belongs to n squared. That is n cross n or n squared. Now whenever we have this infinitely many, I think at the back of our mind we can think that we have seen this infinitely many or infinitely often in case probably what is known as Borel-Cantelli lemma. So let's see, there is a chance that Borel-Cantelli lemma might be used to solve this problem. Let's see. So what is the problem? We have to show that m of E equals to 0, where m is the Lebesgue measure on the real line, which is defined as m of AB equals to B minus A for all A less than B, AB belongs to R. Let us first denote, since you see that in the definition of the set E there are two quantities P and Q. So let us denote first define another set EPQ, which is equals to x belongs to 0 to 1 modulus of x minus pq less than 1 by q to the power alpha, 0 less than p less than equals to q. Now let's just do a simple elementary algebra with this mod and inequality sign. So modulus of x minus p by q less than 1 by q to the power alpha means p minus p by q minus 1 by q to the power alpha is less than x less than p by q plus 1 by q to the power alpha. Thus we have, now if we take, this helps us in finding the Lebesgue measure of EPQ, which is nothing but this upper limit minus the lower limit, that means 2 by q to the power alpha. So we get a concrete value in terms of in a real number value of measure of EPQ for every p and q, and remember this is independent of p. This is a very interesting point to note. Now we just directly apply Borel-Cantelli lemma. We have for alpha greater than 2 summation over all pq m EPQ, which is less than equals to summation k q equals to 1 to infinity twice q plus 1 by q to the power alpha. It's a little bit of algebra, if we do we can get it, and which is less than equals to summation q equals to 1 to infinity 4 by q to the power alpha minus 1. Note that alpha is greater than 2, so alpha minus 1 is greater than 1. That means this entire quantity is less than alpha. So that actually proves the result. So again we have discussed today 4 problems, and we have seen that all the solutions, most of them, they can be solved, some of them at least, using just by direct application of Fatou's lemma. So that actually gives us the idea or that Fatou's lemma is an extremely important lemma or result in measure theory or probability. And similarly, Borel-Cantelli lemma is extremely important. So as I have already mentioned that whenever in a result, if we see some kind of less than equals to or limit, we can think of that, can we apply Fatou's lemma? Or if we see some kind of convergence or some kind of events that are occurring infinitely often or infinitely many times, then can we start thinking that whether Borel-Cantelli lemma would be a good start to solve this problem? It might not be, but in most of the cases it really helps us a lot. So our discussion today are focused only on applications of this very important lemma to some very specific problems, not really known theorems but to specific problems. And please remember that how we have used the techniques that we have used in different parts of a problem or the solutions of a problem.